Hey guys. So what we're going to learn about today is this idea of proteins. It's the third of the macromolecules. We've thus gone through carbohydrates, we've done lipids, and now we're into proteins. And proteins is going to be one of the tougher ones. It just has some stuff uh, to it that are it's very important for this chapter and for the overall understanding of biology. But you can see the alternative name next to proteins right here called a polypeptide. And the reason poly you're going to see is many. At this point, peptide is a new word for you, but you're going to see very quickly when it's used and why it's associated with proteins. As always, we kind of start with that building block or monomer, which is not really a new term. I think we've actually used it a few times, and people have it in their background knowledge of an amino acid. And here's a picture of it. And if we look here, we're just going to look at the components of it, the elements that are there. And if the amino acid has these elements, then you can kind of guess that all proteins would have these elements if these are the building blocks of that larger macromolecule. Let's start with this central carbon, as it's called. And we know that carbon is always going to have those four bonds. Here we have four single bonds to it. The left-hand side, we have a recognizable functional group right here. And you should know that's the amino functional group because it has that nitrogen. So you can kind of see where they're getting the name. Amino for acid, the amino group is what's attached here. On the right-hand side, we have this carbon and a double bonded O and OH. That's our carboxyl group, and they are commonly referred to as the acids. So the name amino acid actually comes from the two major functional groups within this building block. The third bond is to a hydrogen, standard. The fourth bond to this central carbon is recognized here as an R. It just is a variable because there are 20 different amino acids that build proteins. And the only thing that changes from amino acid to amino acid is what it gets attached at this point. We're not going to go through and have to memorize anything. You just are going to see, if you ever see a full picture of an amino acid, you recognize it because every single one of them will have these three bonded parts to the carbon. This could be as small as a hydrogen. It could be larger. It could have an actual ring of carbons. We're not going to get into that detail. This is just letting you know that there are 20 different attachment sites that could be attached right here. And that's what literally makes the difference between the first amino acid, the second amino acid, so on, all the way up to 20. The elements that are present, these are the ones that are present in proteins. And you can see why the first four must be present because we have the carbon that's going to be in every amino acid, so it's going to be in proteins. We have some hydrogens around here. We have some oxygens over here and nitrogens. But notice in parentheses, it's sulfur because not every attachment for this R group contains a sulfur. If it's just a hydrogen, that amino acid doesn't have a sulfur, so therefore sulfur wouldn't be in the chemical equation. But the larger the molecule gets, the more amino acids you're going to get. And I think two of them actually have a sulfur, and maybe you can guess which functional group is attached then. We talked about the sulfhydryls. So some of these R groups must contain sulfhydryls, which if that's the case, then that chemical formula would have an S. Over here we have two words, essential and non-essential. In your everyday vocabulary, you probably think of essential meaning needed and non-essential not needed. So some students immediately think that essential amino acids are ones you need and non-essential are the ones that you don't need. But that's so far from the truth. You need all these amino acids because they build the proteins. What the difference between these two words is where you get these amino acids. Some amino acids you don't need to worry about because your body synthesizes them automatically. So they're non-essential to kind of worry. That's how I kind of think about it. It's non-essential amino acids are ones that you will make automatically, so don't worry about them. Essential amino acids are ones that your body doesn't make, so you have to get them from alternative sources like your diet. So that's where these two words come up, and if you don't think about it, you're going to revert back to what most misconceptions will be based on the vocabulary that you've used. And essential and non-essential, please think about it. So the next thing, we have our monomer. So let's show how it actually builds to be a macromolecule. The ever important process, which you can see highlighted here, which is dehydration synthesis. We're going from two smaller amino acids not chemically combined. We're going to look at the OH group from the left-hand amino acid and the H off of the right-hand amino acid. and we're going to dehydrate these two. So that is going to pull this water out, and now look at this bond that forms right here. That connection from the carbon to the nitrogen is a new bond that only formed because we dehydrated this portion out, and that's called a peptide bond. So now we relate back up to the top here, polypeptide. The peptide bond is what connects amino acid to amino acid. So if we did this over and over again, you're going to get a lot of peptide bonds. All right? One of the most important examples of a protein is an enzyme, also known as an organic catalyst. I think you're very familiar with this term catalyst. What they do is they speed up a chemical reaction. So here's just a very, quick representation of how enzymes work. This x-axis kind of represents time, and as a reaction occurs, we kind of are going through the process of time. In the beginning of time, or for this reaction, this is where we are. The amount of energy required to hold all the bonds together at the beginning of the reaction are all the way up here. And I didn't quantify the y-axis, but you can see relative that it's higher right here than it's going to be at the end of the reaction. So you start here at the beginning of the reaction. So these would kind of be the reactants of the process. Reactants and products that before versus after. So these reactants right here have a relatively high amount of energy that it requires. The amount of energy at the product side, which is later in the reaction, kind of after everything occurs, you notice there is a lesser amount of energy required. Now, an enzyme's job is to help lower the amount of energy required to go from reactant to product. If we follow this graph, we see that there's this little hump right here. And what that represents is the input of energy required to go from reactant to product. And you could measure, if I kind of went from the cursor here to the cursor up, this is what it would take without an enzyme. And if I quantified the y-axis, you would be able to see how much energy you need to put into the system, whether you have to heat that, like heat is a form of energy. So heat could be the supplier of this. There's different ways that you can input energy into a system, but heat is going to be your most common. But with an enzyme, notice what happens to the amount of energy required. It lowers. So that lowering speeds the process up. It's going to take you less time. If you were thinking this is like a hill, the amount of time it takes you to go from here up and over is going to be longer than if the hill was lower. It just makes common sense, hopefully, to realize that the amount of energy to do this hill is less than this. It doesn't supply energy. It just says that you now have to input less of it to go to the product. All right? The lower the activation energy. This amount of energy, they call it activation energy because that's technically what you're doing. You are activating the process. So you need to put this into the system before you can go from the reactants to the product. All right, so that's kind of what an enzyme's purpose is. Without enzymes, you can still get from reactant to product. You just have to put more work into it. And why do all that work if you have this molecule that can kind of do the job at a faster or kind of less energy rate? Okay. The next thing we're going to look at is enzymes sometimes work with chemical reactions to either bring reactants together to make one large product, or sometimes they break one large product into smaller subunits. So here's an example. This molecule is our example enzyme. There's different parts to this enzyme that we'll talk about. This shape, I obviously drew it very strategically, that it's got a very particular shape. It's called the active site. An active site is the location on the enzyme where these reactants, in enzyme language, they often use the term substrate. It's just an alternative word in the context of enzymes. They tend to use substrate as opposed to reactants, but they are in essence the same thing. So these two molecules, think of any reaction that we could kind of think of. Let's think of an example like two monosaccharides. This could be glucose and this could be fructose. They both have a different shape. They have the same chemical form. We talked about that, but they have a different shape. So if we have an enzyme that is specifically using the process to bring glucose and fructose together, That would actually make a disaccharide. It technically makes sucrose. So what will have to happen is there is a specific enzyme. The whole idea of enzymes is this term specificity. They are very specific to the substrate that they work on. Any old enzyme just doesn't work with any old substrate. They often use this term lock and key because a certain key opens a certain lock. You just can't throw any key into a lock and expect it to open. You need a specific enzyme to work with these two substrates because the active site is built specifically for these substrates. So what will happen, you'll notice in the middle picture here, that the substrates will bind to the active site. We don't get into the technicality of what an enzyme does at the molecular level, but what is happening here is it's lowering that activation energy so that these two molecules could then combine into the final product, which in this case is going to be sucrose. It's a disaccharide. They unwind or unbind from the active site, and that then is your product. This is what's known as an anabolic reaction because you're going from two smaller units to something larger. If you ever use the term anabolic before, it might be in front of the term steroid, and I think of anabolic steroids build you up, they make you bigger. So that's how I remember the term anabolic reaction, going from something smaller to one larger product. This enzyme is recyclable. This doesn't mean it's like once it does one reaction, it's done. It actually will go back, and if there's more substrates that have identical glucose and fructose, this enzyme will help again. So it just goes back and forth, helping things out. If you reverse this process, a catabolic reaction is if you start with sucrose and use an enzyme to break it down into its individual monomers, which would be glucose and fructose again. So sometimes you want to break things down. If you need the energy out of it, you'll break it down. If you want to store the energy, you're going to store it in a larger molecule. All right. So that is where we kind of are at this point. I just wanted to do this to get a good overview if you were absent or anything like that, but hopefully that helped.